Science Field Training and Research Program at the Zuni-Bandera Volcanic Field.
Thanks, Kurt. Okay, buckle your seatbelt. I've got a lot of slides because I'm basically showing a lot of pictures of a field site that we're going to be using to help train some undergraduate students. So this is a small group of us. David Crane, Brent Gary, and Larry Crumpler are going to lead this excursion later this year. And so this is building on some of the work that David did with the Center for Lunar Science and Exploration as part of his current survey team, Inner Solar System Impact Processes. So this is a picture here of the Zuni-Bandera volcanic field. This is near Grants, New Mexico, is the little city right here off of Route 40. How do we forward? Okay, well, anyway, it's a great site. We might stay on this slide the whole time. There we go. Okay, so the first point that I like to make is why do we go out and look at the morphologies of what we're looking at? Well, this kind of generalizes the process that we're dealing with. The real key we want to get at is what active process produced the surfaces that we see. So we can go to places like Hawaii where lava is actively being emplaced, and we can look at the textures that we see. And then we can go to other places. For instance, here in New Mexico at the Carrizozo lava flow, we can look at and find similar textures. So most folks are familiar with Pahoehoe ropes. Then you can go to the next step, which is this is serving as the ground truth for remote sensing data. So now you can apply what you've learned at specific areas and broaden that through mapping techniques and using remote sensing data to try and understand relationships across flow fields. So this step here is not all that different from taking it to a different planet. So for instance, the moon. And I'll talk a little bit more about Ina D at the end in relation to some of the flow features that we'll be looking at in New Mexico. And then once you can follow this whole way back to the very beginning or just make the extrapolation to process, if you can make some under good assumptions about what those textures are on the surface. So we will be going to the Zuni-Bandera field in September, and the point that we can drive home here is the range of different volcanic structures and textures in the field. So most people are familiar with lava channels and lava tubes, and hopefully my slides will catch up to me in a few minutes. But the other feature that is a common emplacement style on Earth as well as planets is the emplacement of lava sheets. So we'll be talking about lava sheet emplacement a good bit. So we spend basically a day showing the students the types of features that are common, well known in textbooks and introductory classes like channels and tubes. And then we will be giving them a full day of looking at lava sheets before we then start encouraging them into their own research projects with us on the site. So this is just an example map of the Zuni-Bandera volcanic field, and essentially what we have here is many tens of small volcanic vents. So we have cones and low shields, and the youngest of the lava flows, which are in color here, are several tens of thousands of years old. So this is a great site because you can see really young lava textures, but you can also kind of step back in time and look at how comparable textures degrade and erode through time or become buried, which are all relevant topics for interpreting planetary surfaces. So as I said, most folks are pretty familiar with open lava channels, maybe the enclosed lava tubes. Sheets is one of the concepts that we can really drive home when we get to New Mexico. Sheets, for those who aren't familiar with them, are basically large tabular units. They can be common at the flow front, and this is basically a place where these budding toes are essentially at the flow front breaking out and advancing the flow, but behind that you have basically a continuous liquid core of a sheet with a crust on top of it. Associated with that then are the textures. So we talk about the structures, the channels and tubes. The textures are also information on the surface of the lava that's recorded as that lava cools and freezes into place. So we talk about some of the textures out there, Pahoehoe. A concept that maybe folks aren't as familiar with is Disruptive Pahoehoe, which we can extensively show at the field. And this is related to the sheet process. So you can imagine a sheet like this is forming. As it's getting wider and wider, it's harder for it to expand in all directions. So in some ways, it starts to stall out. If you can get a surge of liquid into that core of that sheet, what happens is this fragile crust on top essentially fractures and breaks and is drug along on the surface of the lava flow. From remote sensing, it looks like a rough lava flow. When you look at a rough lava flow from remote sensing data, it's very easy to conclude that it's an flow. But in many cases, things that we see on other planets might actually be disruptive Pahoehoe, in which case the emplacement process is very different. We're getting at rates primarily. So this is some of the important aspects that we're going to be trying to drive home to the students when they get out there. Now the interesting thing about sheets is as the advancing front starts to stall, there's still liquid coming into the core. The only way to advance at that point is up, unless you break free and make a new advance. And so this is the concept of sheet inflation. So inflation is a recognized process long before scientists really started digging into this. In Hawaii, it's not uncommon to see walls and barriers that have actually stopped lava flows and driven inflation. So here's Jim Zimmelman standing on the edge of a lava flow behind a wall where you can see that the flow is actually inflated high above the wall where it initially encountered it. So here I'm going to run a video, hopefully. Oh, there we go. Great. This is a sheet that we were looking at. In real time, it's easy to focus on the action at the flow front here. So this is where the breakouts, it seems like this is the activity. Can we run that one more time? But when you look at it in fast speed, what you see back here is that the entire sheet is essentially being lifted as the front stalls out. So as you see less red stuff on the front, you see that the sheet itself is inflating. So in Hawaii, it's not too difficult to capture this at the scale of 1 to 2 to 3 meters of inflation. So this is the concept we're going to be talking about. For the inflation part, we're going to focus on the McCarty's flow right here, which is a basaltic lava flow. It's a 48-kilometer long lava flow. It's one of the longer ones in the continental states. It's only about 3,000 years old, which is pretty young for basaltic lava flows in the southwest, so the textures are pretty well preserved. It's classified as a compound tube-fed Pahoehoe lava flow field, which basically means it's pretty complicated. There's a lot of things going on in there, and that's what we try to tease out when we work on these flows. So I'll talk about some of the structures that we can see. Down here in the southeast corner, we get these flat-topped plateaus, and here's a slightly broader view of that, or a more detailed view of that. You can see these flat-topped surfaces up here marked by these irregular edges, and then there are irregular depressions on the interior. As you get into the flow field, we'll look at a couple spots here. These edges look like this. So this is Larry Crumpler and Jim Zimmelman standing at the base of a flow margin, and you can see that these things are quite massive. So when I talked about the lava flow inflation in Hawaii on the scale of 1 meter or 2, here we see it on the scale of over 10 meters. It's quite impressive to walk up to a wall of tilted basalt that's just straight up. But the question has always persisted, well, maybe that's the flow front. Was this a 10-meter high lava flow advancing as a 10-meter thick lava flow? And that's the concept of flood emplacement. So if you think about flood lavas, the concept is that you've got these tens of meters thick lava flows that are just hauling forward, and that's where that flood term comes from. Here's an example of Brent here at the yellow arrow dragging our differential GPS up one of these things, and you can just see how impressive these features are. This was a differential GPS of that. Here's Brent at the bottom. This one measured up to about 14 meters, so it's a pretty impressive wall of rock when you get out there. Now, to accommodate that uplift, you basically have to form large cracks in that crust. So almost always along the margin of one of these rises, you will encounter these clefts. And it's really disorienting sometimes to be walking across a plateau and you kind of get this sense like, all right, yep, I'm on the ground here. And all of a sudden you run into a crack that's 8, 9, sometimes 10 meters deep. So these are the cracks that as that lava flow that was initially down here tens of centimeters thick starts to inflate, that rigid crust has to separate to accommodate the uplift. And so you drive these big cracks, and these are features that are common throughout the flow field. Within the plateaus, you have a number of irregular shaped pits. And so you probably most of you have seen me talking about this, trying to understand pit formation on other planets. Not always are pits linked to lava tubes. In many of these cases, these are pits that are not linked to caves or tubes in any way. So these are the type of thing that we'll be able to show them when we get them out into the field. Some of the textures that are quite common is this lineated type of texture. It's very common here. This is a flow direction indicator. These form along shear zones on those lobes, those toey fronts. The thicker parts flow slightly faster. As they're cooling, they start to preserve these shear zones in a lineated texture like this. Within the lineated texture, then, it's not uncommon to get these coils. So if you start to have little clots or sections that are more cooled off than others, as they're crossing through those shear zones, you can actually spin them, and you get these lava coils, lava rows. They have all kinds of names. But these are really good indicators to us of what exactly was happening there, that this is not, this is basically telling us that the whole part of that sheet was cooling together as it was advancing, and you're getting some of the shear zone preserved. We have lava ropes, which are common throughout the flow field. This is where it gets interesting. We get into the slabby, rubbly stuff. So I showed the picture of the Disruptive Pahoehoe at Hawaii a little bit earlier. This stuff is common all throughout the plateaus. You'll have very smooth Pahoehoe, and then you'll grade into these slabs. One of the things we've been trying to do is measure the slabs, because with the cooling rate, you can actually start to guess at how long that crust was cooling before the next disruption pulse came through and disrupted it. So this really gets at the timing and emplacement rates for some of these lava flows. Now, along with the cracking that we see, those clefts I was showing you, sometimes you can get these blade-like wedges that actually squeeze out of the cracks. So you can get these on cracks that are growing up, but you can also imagine and see here that as that crust is being driven up, if there's a void space or a pit, you actually get these lateral wedges that come out. And sometimes they actually drape down. They can start to bend down, so they're still somewhat plastic, obviously, as they're coming out. And a lot of times you'll see tool marks on these from the wedge that was there before them. Very interesting details about this. Within lava sheets, we have these vesticulated zones. Again, if you think about a crust on the top and you get fresh pulses of lava coming through the system continuously, they're degassing. Those bubbles will come up. They'll collect along the viscosity zone that marks the crust, and that we get to see these. These are very diagnostic of what we're looking at. We also see some of this crust separating as plates. You can see it on small scales like this right here. You can actually see it on very large scales on some of these margins. So you can kind of put these things back together as puzzles. Again, indicators of that crust on top of a liquid core. The buckling of the crust in some places to accommodate a lot of this movement that's within the sheet. The textural changes often are very abrupt. You see Pahoehoe here and slabby lava right beside it. So what we're really going to be getting at with the students is trying to understand the emplacement history. Did inflation really drive some of these features? How did the pits form? What are the characteristic versus diagnostic features that we see? What were the pathways that the flow experienced? This is one of our current understandings, we think, of what's going on, and it's just basically this emplacement of a sheet, formation of a crust, thickening of the interior of the sheet, and disruption of the crust on the surface. Pit formation, again, I've talked about this at other meetings, but it's relevant to us for looking at other planets, because we really do want to know if the sheet is coming around an obstacle and then it inflates, you basically form a pit with no access to protective pathways beside it. So this becomes pretty important. Other things, trying to understand where breakout zones happen. These flow fields get very complicated. You can have a lobe here and a lobe here, and if this one inflates, it actually drags up this edge of the other lava flow. So the superposition gets extremely complicated. So we like to use these as examples of how the layer cake isn't always exactly the easiest way to interpret volcanic terrains. Let's just bring this back around. Inflated plateaus. Brent Gary and I and several other people wrote a paper a few years ago suggesting that INA D and features like that might actually be representing inflated lava flow processes. So this is an important place for us to try and understand that. And again, this gets back to a number of big types of questions. Inflation enables emplacement over very long distances because you preserve the thermal properties of the lava. It's not cooling right away. This occurs in all styles of basaltic terrain development. Planetary inflation could probably be inferred from characteristic features. So these pits, these plateaus, the relationships between them. And then the textures are things that we're now starting to get into. And this is also important because we're now seeing that impact ejecta sheets, which are liquid in some cases, have a lot of common textures. So Kelsey Young and I, the previous speaker, have a session at GSA this year comparing lava emplacement processes with impact crater ejecta deposit processes. So we're working on these processes. We're trying to understand them from a volcanic side, and we're hoping to integrate well with the impact community. So if you're interested in that topic, pay attention to GSA. Thank you.
No, you're good. In the interest of time, just maybe one quick question for Jacob.